let me describe a little bit about universality. In the language of the circuit model of computation, because that's what we naturally know best, and also is what we will build quantum computation upon as a language. So in the circuit model, for example, we may have AND gates and NOT gates. And I want to claim that all Boolean circuits, circuits that compute Boolean functions, can be composed of AND and NOT. And this is fairly easy to see. But first, let's look at the family of Boolean functions. They will be functions that take, if there are n bits of input, say x0 to xn minus 1. And the result of this is going to be either 0 or 1. OK, so for example, in the notation, I will say that we may have f of x1, x2 be x1, x2. And this product represents an AND gate. Or, for example, f of x is equal to x bar. And this is how I will represent a NOT gate. OK? Now, the question of universality dovetails with another question. And I haven't finished the universality description yet. But I want you to keep this in mind of complexity. Because it's not terribly useful if I say something about universality without saying how much cost it takes to accomplish something. So here, the key idea is that, which we will not have time to go into much depth on, but I hope you already know something about, which is that some math problems are harder than others. Apparently. And I don't mean it's hard to multiply two million-digit numbers, and that's harder than multiplying two 10-digit numbers. No, that's not the point. The point is they're scaling with respect to the size of the problem. And this leads to a statement which I hope that all of you already know in some form, which is called the strong Church-Turing thesis. And I'll write this up for you because I think the words of this are very useful in understanding the perspective. So we say any model of computation can be simulated on a specific kind of machine. And the machine and model I would choose will be this one here, the Turing machine. But I'm going to choose a specific variant of it, the probabilistic Turing machine. And I need to say something about the cost of this kind of simulation. And what I mean, the thesis of this statement is that, and the essence of that thesis is that this simulation cost comes with, at most, a polynomial increase in the number of elementary operations. Required. It's an extraordinary thesis. It defines an equivalence between models, whether they be electrical and optical, or electrical and DNA, or quantum and DNA, or quantum and classical. And for even that to be possible conceptually is remarkable. And I haven't defined a lot of the technical terms in this, like simulation and the overhead costs. But I hope you'll get to appreciate that as we go along. OK, so now in order to highlight this statement of equivalence, let me make sure you are aware of one of the greatest motivating factors for quantum computing, which is the difference between two of the most important classes of mathematical problems. And for this, I'll use this fact that many problems can be expressed as decision problems. So for example, is the number m prime? And the answer to this is yes or no. Is this a hard problem or an easy problem? This actually was not known for many years. It was then realized that you could answer this question with some randomness. You wouldn't know it for certain. This is Rabin's primality testing algorithm. And then some 15 years ago, somebody in India proved that you could do it deterministically. So it moved from this probabilistic model, which people had to use previously for this question, to something which did not need probability. So today there is a deterministic primality testing algorithm. And this problem is called primality. OK, so that's one example. Here's another one. It's called factoring. Given a composite integer m, but not just the number that we're going to try to factor, also and a number L, an integer L, which is larger than, less than m, does m have a factor that's non-trivial which is less than L? So we need to bound the size of the range of numbers we're going to consider as being answers to the problem. And again, this is a yes or no question. And we have this distinction. If the answer is, let me do this. If the time taken to answer this question, needed to answer this question, is polynomial in the size of the question. And here, for example, for factoring, this is the number of bits of m, the number of digits in the number. Okay, it's not just the size, the number itself. Then we say that the problem is polynomial in complexity. So we say it's in this class that we'll call P. OK. Now, let me break down the class of whether this is something answered by a yes or by a no. If the yes instances are of the problem are easily checked, I'll use the word verified as a technical term, with the aid of a witness, which is a short description piece of information that enables somebody else who's not terribly skilled at the arts but can be very reliable to verify your claim. Sometimes we talk about a Merlin and an Arthur. We say that the Merlin is somebody who's very clever and can come up with proofs. But you need the Arthur who's not terribly clever but can be very, very reliable to take that proof and verify the claim. So there are two parties to this, the verifier and the prover. and the verifier takes this witness, then we say if this is true, then the problem, even if it is very difficult, the fact that we can verify the proof of it means that we will say that the problem is in this class called NP. And in some senses, I want to say this is non-polynomial. But the main point of this is the distinction between P and NP. And for sake of completeness, we have another parallel to this, which is the mirror image. If no instances, so this is the answer is yes, and this is the answer is no, with exactly the same language, then we say that the problem is in a different class called co-NP. And I do this not because I want to say anything more about P versus co-NP or NP versus co-NP, but just to share with you a trivial fact in a moment. So the reason I show this is because so much of the motivation for computation today and much of quantum computation comes from this question of NP versus P. We think that the P problems are easy and the NP problems are the hard ones and meaningful ones to do. And there's this plot that you can make which shows that if this is the space of all mathematical problems, then P is a subset of something we might see as NP. But there's also this extra area over here, which is the hardest of the NP problems. We call these the NP complete problems. And they're defined as such because if you can solve any of the problems that are NP complete, then it gives you a polynomial time algorithm to solve any of the other problems in the NP regime. So where's quantum computation in all of this map? Well, I'm not going to answer that for you today, but I hope that through the course of this class and this semester, you'll start to appreciate where quantum computation is relative to this landscape of the field of all problems and their complexities. Okay, quantum computation sits kind of differently in this landscape. It has a complexity class typically of something we call BQP. And part of the reason for that is because the model is slightly different and doesn't fit directly into either of these classes because sometimes the output is quantum mechanical, there are errors involved, and some things we'll come to later. Good. So I hope many of you already knew about most of this, but I also hope that it starts to connect some things for you. An example of an NP complete problem, and now I'm going to go back to the concept of universality, is so an example is a problem called 3-set. And this is about the satisfiability of Boolean functions, which look something like this. So suppose you have, again, a function of bits x0 through xn minus 1. And the formulas that are involved in 3-set look something like x1 plus x3 plus x9 OR together, ANDed with, there's a multiplication here, another term like x4 plus x7 bar plus x11, and so forth and so on, where each one of these terms just has 3 bits. And your goal is to say, does there exist an assignment of zeros and ones to the x inputs such that the output is equal to 1? Seems very simple. It's very easy to write this problem on the board. But if you can solve this problem fast in time that's polynomial with n here, then it turns out you can solve all the rest of these problems fast. And in fact, if you can solve this problem fast, you can solve problems like the optimum way to pack boxes into a FedEx truck, or the optimum way to route a packet of information from San Francisco to Boston. You know, it's really remarkable how powerful such a simple problem can be. And yet I can show that in practice, you can't really solve most of the instances of this problem as well as we would like to. Yes, please.
Are there simple problems that are neither P nor NP?
Are there simple problems that are P neither P nor NP. Yeah, so another interesting class that sits outside of this is the class of counting the number of solutions to a problem. That's the class called sharp P, and so on and so forth, because you might count the number of things to count the number. Okay, but this is how you get a career as a theoretical computer scientist. It's very effective. Other questions?